On paper, a 74-ton main battle tank should be a logistical nightmare. Its gas turbine engine drinks fuel like a fighter jet at idle. Bridges in much of the world will collapse under its weight. And yet, here we are, U.S. Marine expeditionary units rushing heavy armored vehicles toward one of the most volatile choke points on Earth. For decades, engineers have slammed into the same brutal constraint. You cannot simultaneously maximize protection, mobility, and firepower without breaking the laws of physics. Today, as tensions with Iran escalate and Marines position heavy combat vehicles, we're watching that impossible compromise play out in real time. Maps of the Strait of Hormuz, oil flow graphics, Marine expeditionary unit loading footage, amphibious ships. The driver is brutally simple. Control of energy. Roughly 20% of the world's oil passes through the narrow Strait of Hormuz. Disrupt that, and global markets feel it instantly. When air and naval strikes alone may not suffice to secure shipping lanes or key terrain like Karg Island, commanders turn to ground forces that can actually hold ground. Marine expeditionary units are designed for exactly this. Rapid insertion from the sea, bringing their own air power, logistics, and now heavier armored punch. Reports show Bradley fighting vehicles and, in supporting Army elements, M1 Abrams tanks moving into theater. These are not light expeditionary toys. They are 30 to 74-ton machines built to survive and dominate against determined opposition. Why heavy armor now? Because modern battlefields are lethal. Drones, anti-tank guided missiles, and artillery can turn lightly protected forces into statistics very quickly. Heavy vehicles provide the standoff protection and direct firepower needed to maneuver under fire. Cut to slow-motion tank acceleration, then animated cross-section of the M1. Let's go first principles. Protection starts with stopping kinetic energy. A modern anti-tank round might deliver over 10 megajoules on impact. That's like a small car hitting you at highway speed, concentrated on a few square centimeters. Steel alone, you'd need hundreds of millimeters of thickness, making the tank immobile. So engineers turn to composite armor. Layers of steel, ceramics, and, in the Abrams case, depleted uranium mesh inserts. Why depleted uranium? Density. At 19.1 G/cm superscript 3, it's 70% denser than lead. When a high-velocity penetrator hits, that density disrupts the jet or rod, eroding it before it reaches the crew. The ceramic layers shatter the incoming projectile, while the metal backing catches fragments. It's a multi-hit system that exploits material science at the molecular level. Ceramics excel in compressive strength, but are brittle. Metals give ductility. But every gram of armor adds weight. The current M1A2 tips the scales at around 74 tons. That mass demands enormous power to move. Enter the AGT 1500 gas turbine. 1,500 horsepower in a package that weighs only about 2,500 pounds and occupies less than 48 cubic feet. Compare that to a diesel of similar output. It's dramatically smaller and lighter. Why a turbine? Thermodynamics. In a gas turbine, air is compressed, fuel is burned continuously, and hot gases expand through turbines. There's no reciprocating mass, so it spools up instantly and delivers torque across a huge RPM range. The Abrams can go from 0 to 20 miles per hour in about 6 to 7 seconds and hit governed speeds over 40 miles per hour on roads. That agility is physics in action. High power-to-weight ratio lets the tank dash across kill zones before enemies can react. Side-by-side power curve graph, turbine versus diesel torque band. But here's the catch everyone knows. Fuel efficiency. At idle, the AGT 1500 can burn 15 gallons per hour. In combat, a tank company might need refueling 3 times a day. Jet fuel or diesel, both work, but you're hauling thousands of extra gallons just to keep these beasts moving. Exploded view animation of the AGT 1500, then Chobham armor layers, then suspension animation. Engineers solved the power problem by borrowing from aviation. The AGT 1500 is essentially a simplified aircraft turbine, multi-fuel capable, with a recuperator heat exchanger that recaptures exhaust energy to preheat incoming air, improving thermal efficiency. For armor, it's not just slapping on more metal. The classified special armor uses space layers and materials engineered to defeat specific threats, long-rod penetrators from tank guns and shaped charge jets from missiles. Depleted uranium's high density and self-sharpening behavior, when used in ammunition, also apply in reverse for defense. Mobility, advanced hydropneumatic suspension, and wide tracks keep ground pressure manageable, around 13 to 15 psi, so the tank doesn't sink in soft soil as badly as you'd expect from its mass. And the Bradley? At roughly 30 to 35 tons with conventional diesel, it's a lighter, faster escort that carries infantry and 25mm cannon fire support, letting the Abrams focus on the heaviest threats. CFD simulation of airflow over tank hull plus thermal imaging of engine exhaust. The real engineering genius is integration. Fire control computers that stabilize the gun while the tank bounces at 30 miles per hour, thermal sights that see through smoke and dust, and compartmentalized ammunition storage that dramatically reduces cook-off risk. Nothing is free. The Turbine is thirstier than a comparable diesel, often cited as 50 to 90% higher consumption, depending on conditions. That means longer, more vulnerable supply lines. In a contested environment like the Middle East, every fuel truck is a target. Weight restricts strategic mobility. Only certain ships, aircraft, M1 Abrams per C-17, and heavy bridges can handle it. In urban or mountainous terrain near the Strait, that 74-ton behemoth can become a liability if roads are damaged. Maintenance? Turbines are simpler in some ways. No pistons, but hot section components need careful handling, and the whole power pack is designed for rapid swap, not field tinkering. The Bradley trades some protection for speed and troop capacity. It's not meant to slug it out with main battle tanks one-on-one. Marketing sometimes calls these invincible. Reality: every system has vulnerabilities. Top attack munitions, drones with tandem warheads, or simply being swarmed when isolated from infantry and air support. Current footage of marine vehicles, cost overlays. So, is this deployment viable? Yes. For short, high-intensity operations where sea-based logistics can sustain the force and air dominance suppresses enemy long-range fires. Marine MEUs bring organic aviation, F-35B helicopters, that helps offset the armor's logistical thirst. But scaling to a prolonged ground campaign would be enormously expensive. A single M1 Abrams costs around $10 million. Keeping a company fueled and maintained in theater multiplies that rapidly. The U.S. military's ability to project this power rests on its unmatched logistics backbone, something few nations can match. Future designs like the planned M1 E3 aim to cut weight and fuel use by 20% while keeping protection. Materials science, better ceramics, active protection systems, may eventually square the circle. Wide shot tank silhouetted against horizon. Thoughtful music swell. Heavy combat vehicles like these remind us of engineering's core truth. Nature doesn't negotiate. Every extra ton of protection steals from mobility. Every horsepower gained exacts a fuel tax. The Abrams and its companions exist not because they're perfect, but because they represent the best compromised physicists and material scientists could forge under the unforgiving constraints of combat. Human ingenuity keeps pushing those limits. Whether in the deserts near Hormuz or the labs back home, the question remains the same. How much protection can we buy without losing the ability to move and fight? That's the real engineering story behind the headlines. Subscribe, like, comment what engineering trade-off. Thanks for watching. Stay curious.